All right, we'll get started today. So the exam is finished, and you can see your results now in Blackboard. If you weren't sure how to do that, they should be available starting today, and you just have to go in through the gradebook and click on the score in the gradebook, and it'll take you to your results. So not through the exam folder, but through the gradebook is how you get to that. So if you have any questions on how the exam was graded or why you missed something, or just want to know what you did wrong, then please come find me, and we can definitely talk about that. I haven't tallied the averages yet, but I'll do that probably today, and then next week I'll tell you guys what the sort of aggregate scores were. They look fine to me, but that's just a quick glance, so I can't say for sure anything until I run the numbers. Okay, so what we're going to do today, though, is transition into the fifth chapter of our book, chapter 5, and it's going to be a pretty abrupt switch in terms of the types of material that we'll be covering. So up until now, we've been doing... So if you look closely at what the textbook is called, it's called the atoms first approach. We've been doing everything with, first individual atoms and then individual molecules, finishing up, recently with chapter 4, where we talked a lot about the structure and bonding in covalent compounds. And now we're going to move on to talking about sort of at a more macroscopic level. So how chemical reactions happen, how we measure chemical substances that are involved in chemical reactions. It's going to be a lot more numerical and mathematical, I would say. So the first 4 chapters are almost exclusively conceptual, and now the next 4 are going to have a lot of math involved. Not that there aren't concepts as well, but the types of problems you're seeing are going to skew a lot more towards numerical things in the upcoming few weeks. All right, so that's what we're going to start with today is the beginning of chapter 5, which is atomic mass and moles. All right, so the first thing we want to define is atomic mass. Now we've seen this before. So we've been staring at the periodic table quite a bit recently when we talk about electronic configurations and valence electron counts and all that stuff. So the atomic mass is on the periodic table, and you've seen that number, but we're going to give a more explicit definition of it today, and also then more about how we use it, which is the more important part. So the first thing is that there's sort of 2 units that are associated with atomic mass, and one of those is called the atomic mass unit. And numerically the 2 are the same. So whether you use this atomic mass unit or whether you use the more useful unit that we'll give later on, the numbers are the same. But what is an atomic mass unit? So it's when we say AMU, we're referring to the mass of an individual atom, is sort of on that scale. And the way that it's defined is as it takes a standard, which is carbon-12. So if you take the mass of the carbon-12 isotope and then divide it by 12, that's equal to 1 AMU. And so what we're saying is that, as we'll see, atomic mass is related to mass number, which we already talked about, mass number being protons plus neutrons, but the atomic mass does not exactly equal the mass number for any isotope except for carbon-12. So we set sort of carbon-12 as the standard. It's very abundant, very widely studied, and so we say that the atomic mass of carbon-12 is exactly 12 AMU, exactly the same as its mass number, and then everything else is measured relative to that. All right, so that's why we use 12 carbon as the standard. And so every other atomic mass that we would report for any isotope or any element itself is going to be relative to this. And we don't need to really know how these masses are measured, but just a little bit of a background about that. The way it's done is one of the common ways is a technique called mass spectrometry, where you ionize the atoms. So you make positively charged, usually positively charged or negatively charged sometimes. You ionize the atoms in some way, and then you shoot them through an electric field, and they're going to bend towards that electric field. And the amount that they bend is proportional to their mass. And so you basically measure the bend of carbon-12, and then there's a lot of physics behind it, but then you measure any other atom relative to that, and the relative amount then gives you the relative masses. So the way that they're done, again, is in a relative sense. So if you use this sort of mass techniques that I briefly described, you might get, for example, that let's do carbon-13, the other major isotope of carbon. So you might find in a relative sense, so you can't really measure absolute masses of atoms very easily, but in a relative sense, you would find that the ratio of these two is 1.0836. And so then what we would find is, just by a little bit of math, a little bit of algebra, the mass of carbon-13, we just cross multiply. Mass of carbon-12 is exactly 12 AMU, and so when we cross multiply that, we get close to 13, but not exactly 13. So what's going on there? So this is what I already mentioned. We're going to talk a little bit about why this is. That the masses of other isotopes are often very close to the mass number, but not exactly equal. So the mass of carbon-13 is not exactly 13 AMU. It's a little bit different than that. And the further away you get from carbon-12, the heavier and heavier the elements get, the further their masses are of each isotope from the actual mass number. So they are related, but they're not exactly the same. And the reason they're not exactly the same, to transition right into that, why is this not exactly 13, or why are other isotopes not exactly equal to the mass number? It's because of a famous equation that was devised by a reasonably famous scientist named Einstein, which is E equals mc squared. Maybe not quite as famous as I am, but he's pretty well known. So anyway, this is E equals mc squared, and that's this kind of explains why these isotope masses are not exactly equal to the mass number, because when you bring protons and neutrons together to make a nucleus, this is not something you'll really cover in detail until Chem 2, but when you do that, you release a lot of energy. And because of this relationship between mass and energy, when you release that energy in the formation of a nucleus, you also release some of the mass from the nucleus. So it's not exactly equal to the number of protons and neutrons that are in that nucleus. There's some mass loss as a result of the high amount of energy that is involved in that formation of a nucleus. So a lot of energy is released when nuclei are formed. And again, this is mostly just background information, but there's always some confusion. Why don't the atomic masses just equal the mass number? All protons and neutrons are the same. Well, it's because when you form a nucleus, when you bring those protons and neutrons together, you lose some mass in the form of energy. We'll just say changes the mass for now, not be too specific about how exactly it changes, but that's going to be the reason. All right. So that's fairly important to understand, but the more important thing to understand is how do we use these individual isotope masses to get the atomic mass of an element. Because normally when we work with elements or substances that are made out of those elements, we don't have just a single isotope present. If we just had pure carbon-13, we would know exactly what the mass is based on the number I just gave you. But in reality, if we're working with carbon that we get from natural sources, it's going to have a mixture of all of the isotopes of carbon. And so then to be able to define an atomic mass for carbon, we have to take the weighted average of each isotope that's in that sample. And so the two ways we do that, we have to know each isotope mass, and also we have to define the percent abundance. So this is the relative amount of each isotope in a natural sample of the element. So it is possible to artificially prepare isotopically enriched or isotopically pure samples that have a majority single isotope or exclusively a single isotope. But if you have a natural sample of most elements, you dig it out of the ground or get it out of the air, wherever it comes from, in most cases those natural samples are going to have mixtures of isotopes, not just be a single one. And so then we need to define a relative abundance of each isotope, relative amount in the sample. So it's often referred to as a percentage, although the ratio would be just the percentage divided by 100, so both of those are kind of important. And so if we have our carbon example that we've been going through right now, in a naturally occurring sample of carbon, it's mostly carbon-12. It's like 98.89%. So that means in a sample of carbon-12, 98.89% of the atoms, in a sample of carbon itself, just the element, 98.89% of the atoms are carbon-12. So if you had 1,000, I guess if you had 10,000, you have to go that high. If you had 10,000 carbon atoms, 9,889 of those would be carbon-12. But there's still a little bit that's not carbon-12, so the vast majority of the rest is carbon-13. And so that's going to make up the other 1% or so. All right, so it's not the major isotope, but it is still present in significant measurable amounts. So when you have a sample of carbon is this, black substance. They used to make pencils out of carbon, and I think they don't use that as much anymore. But I guess pencil lead, as they call it, still contains a lot of carbon. So that sort of black, or if you have a diamond on you, if you're into jewelry or already married or engaged, then you might have a diamond. and that's pure carbon as well. So that's going to have basically this percentage of each of those isotopes when it's naturally occurring. And then what we do to define the atomic mass for the element, the one that we're going to actually use when we do calculations on these things, is it's going to be defined as the weighted average of all of the isotope masses. And so that's what we're going to have then for a generic element is, if you have isotope A, you're going to need the fractional abundance of that isotope multiplied by its mass, plus the fractional abundance of the second isotope multiplied by its mass. And you keep doing that for however many isotopes make up that element. For carbon, it's basically 2 that you have to worry about. For other elements, there might be more than 2 isotopes, but it's just the fraction of each isotope multiplied by the mass of each isotope added together. And just to keep in mind, the terminology here, fraction is the percentage divided by 100. Okay, so the percentages are always out of 100, but for this relationship we need the fractional abundance, which is just the percentage divided by 100. So it'd be 0.9889 for carbon 12, 0.0111 for carbon 13. All right, so that's how we define atomic mass. And so what that leads to then is there are going to be homework and test questions that just really deal with the definition of atomic mass, not actually using it for anything, but just how that definition works. So here's a pretty typical sample problem where we're going to just use that relationship directly. We have, in this case, boron, which is atomic symbol B, and it has also 2 isotopes that make up the, close to 100% of it. There might be like some tiny amounts of other ones, but these 2 isotopes make up essentially all of it. Boron 10, which has this mass and this abundance, and boron 11, which has this mass and higher abundance. And once again, we see that the isotope masses are close, but not exactly equal to the mass number of each isotope, for reasons we talked about. So when we see a problem like this, where we're giving you, isotopes, abundances, and asking you something about that, we should automatically think of the relationship that I just gave you, which is that the atomic mass is the fraction of each isotope multiplied by its mass. So we have boron 10 is one of our isotopes, and we need to multiply that by its mass. And then we're going to add to that the fraction of the other isotope, which is boron 11, multiplied by that mass. All right, and so you're going to have typically something that's unknown, and here we're just determining the atomic mass. So in order to determine the atomic mass, we have to give you everything else, which we did. So the only difference, of course, is that we're giving you percentages usually, and you have to make sure you use them as fractions. And so when we talk about the fractional abundance of each isotope, if we do it for boron 10 first, remember that's going to be the percentage, which is 19.90 divided by 100. So that's the number we would use for the fractional abundance of boron 10, and by the same argument, the fraction of boron 11 is just that number, 80.10 divided by 100, which is 0.8010. Okay, so those are the numbers we use for the fractional abundance. That's not directly given to us, but it's just the percentage divided by 100. And now we can just plug in all the numbers that we have to find the atomic mass of boron. All right, so the fraction of boron 10 is 0.1990, and the mass of that is given to us as 10.01294. in AMU. And then we have 0.8010 is the other fractional abundance, and the other mass of that isotope is 11.00931. So these types of problems are not too difficult. You just have to make sure that you're matching up the right fractional abundance with the right mass, and that you use fractions and not percentages when you're doing these sort of calculations. All right, and so what that comes out to is 1.993 plus 8.818 for just multiplying out, which adds together to 10.811 AMU. Guess we could probably keep more decimals than that, but that's probably enough. All right, and so that's the number we would get. Now what we can do is we can compare that to the number on the periodic table. So I have to open the periodic table here. So we haven't, we'll get into this more later on, but this number here that's underneath each element, and that's probably kind of small for you right now, but the number that's underneath each element is the atomic mass, which we have not really used yet, but we've seen it. And we can see for boron that's exactly what it is, 10.811. So that's exactly the number that we calculated using the individual isotope masses. So the thing we're going to be doing more often in this part of the course is using atomic mass to do other things. But this is how it's defined, and this is how it would be calculated if you had the masses and abundances of each isotope. All right, now we're going to do just one other one that's the same concept, but just set up a little bit differently. So here we have the element chlorine. So if we looked up its atomic mass on the periodic table, it's 35.45. And it has two naturally occurring isotopes, which are 35 chlorine with this atomic mass and 37 chlorine with that atomic mass. What is the percent abundance of 35Cl? So in this case, we have a different unknown. We didn't give you the percentage abundances. We gave you the other things. We gave you the masses of each, the total average atomic mass along with the isotope masses, and asking you to solve for that. So what we're going to do in this problem, just to keep things a little bit simpler, is we're going to define these two fractional abundances as variables x and y. So I don't have to write, mainly just I don't have to write out fractional abundance a million times. So the fractional abundance of, let's say, 35Cl, the first isotope, we'll call that x, and the other one we'll call y. Again, that's mainly just to simplify the algebra and how much I have to write. Okay, so those are going to be the two fractional abundances. Now, the problem with this is when we have the definition of atomic mass, which is this thing, this equation up here, just swapping out the different isotopes we're talking about, we only have one equation, but we're going to have two unknowns in this. We're going to have each fractional abundance, x and y, both as unknowns. So when we set up that equation, if we say the atomic mass of chlorine is 35.45, I'll just do it numerically, I'll leave the units out if you'll forgive me for that. And then we're going to say that's equal to the mass of each isotope multiplied by its abundance. So for 35Cl, it's going to be that mass that's given to us, 34.96885, multiplied by its abundance, which is x, plus the mass of the second isotope, which is 36.96590, multiplied by its abundance, which is y. So that's the equation we would set up using just the definition of atomic mass. And as you guys know from algebra, if you have one equation and two unknowns, you can't solve it. So we have to always remember then when we're doing problems like this, that there's another simple relationship, which is that however many fractional abundances you have, in this case there's just two of them, x and y, those have to add up to be 1. All right, because the total abundance of the element, or the total percent abundance, would be 100, and the total fractional abundance would have to equal 1. So we always have this relationship. And for problems like this, you're never going to have more than two isotopes, because if you had more than two, unless we gave you one of those fractional abundances, so we're only going to have two unknown isotope abundances at most, and that's going to be how we would solve this one then with the second equation. So what we can do then, well, we're solving for the abundance of 35 chlorine, which is x. So we're going to rearrange this and write y is equal to 1 minus x, and then we're going to substitute that in for y. So whatever your preferred method is for solving systems of equations, but typically this will be the most straightforward way. Figure out which one you're looking for, in this case x, and then write the other one in terms of that, and then do the substitution and go from there. So when we write that out with that substitution, atomic mass 35.45 is equal to the isotope mass multiplied by the first abundance, and then the second isotope mass multiplied by the second abundance, which can be written as 1 minus x. And now we just have one equation with x as our only unknown. All right, so I'm going to save some time and just use the algebra machine to do the rest, and say that what we get is x is equal to 0.7590, but we're asking for a percent abundance, so we have to multiply that by 100 to make it 75.90. All right, and that matches up with choice C. All right, so that's just using the exact same relationship. So that's really the only relationship we're going to have for atomic mass as a definition, which is just fractional abundances multiplied by masses, getting a weighted average, and then just look at what you're asked to solve for and piece together the rest. So any questions on that concept or those two problems? All right. Now, the more interesting thing we're going to cover today is the mole, which is, it is an animal, but in our case, it's not. This is not a biology class. This is chemistry. So what does a mole mean in the context of chemistry? Well, a mole is simply a counting word. As you'll see, the number that it refers to is a bit bigger than the typical counting words we have in the English language, but it's just a counting word. So you've probably heard some or all of these before. There's actually not too many of these that are that common, but if you've heard of a dozen, I'm sure. Which is 12 things. So if you buy a dozen eggs, that's a package of 12, or a baker's dozen is 13. But and then if you have a gross, again, we don't use these terms a lot in everyday language, but you might be familiar with a gross, which is 12 dozen. So a dozen dozens is a gross, which is 144 total objects in a gross. And then one that probably hasn't been popular in at least 100 years or so is score. So if you guys remember Gettysburg Address 7 years ago, well, score means 20, so 7 is 87. He was referring to the revolution that had occurred 87 years ago, and so a score means 20. So these are all counting words in the English language that refer to a number of objects or a number of items. And that's exactly what a mole is. It's just a counting word that we use in chemistry, but the number that's associated with it is, as I said, a bit larger than these. It's 6.022 times 10 to the 23rd. Things, whatever we're measuring, usually it's going to be atoms or molecules, but any chemical entity that we're measuring in terms of moles, there would be 6.022 times 10 to the 23rd of those things in 1 mole of that substance, that object, whatever it is. And this number here is called Avogadros number, as you might be familiar with. Now, I'm not exactly a chemical historian, but what I understand is that the scientist Avogadro didn't actually come up with this number. We talked a little bit about Avogadro earlier in the course. He kind of came up with some ideas that were important for determining chemical formulas of gas-phase substances, and we're going to talk about Avogadro's law later on in the course as well when we get back to gases. So he had a lot of important discoveries in that area, but this number was not one of them. I think basically the story goes that whoever the scientists that came up with Avogadro's number just had a big man crush on Avogadro and wanted to name their number after him. But he didn't actually come up with it himself, but he still gets the name. All right, so that's called Avogadro's number, and that tells you how many things are in 1 mole. So the next slide I'm going to do is purely just to help you understand how big of a number this is. This is not going to be anything that's going to come up on a homework assignment or test or anything like that, just to give you an idea of how big this number is. I think this is fun anyway. But again, you and I have different definitions of fun, but we'll see. All right, so let's say we took 1 mole of M&Ms and we were going to stack them over the entire United States of America. So we're going to lay them down next to each other, so they're all right next, perfectly packed layer, stack them over the entire United States of America, and then we're going to keep stacking additional layers on top of that until we've finished up our mole of M&Ms. Now, does anybody have a guess for how many layers that would be? A lot. We mean more, yeah? 20 layers. Okay, we have a guess for 20. Anything else? 5. All right, so we got numbers in that range now. If we want to use a whole mole of M&Ms over the entire United States, we're going to need like 5 to 20 layers. Let's see how close you guys are to being right. So the way that you can estimate this, I'm not going to go through the math in detail, but just where these numbers come from if you want to check me on it. The volume of 1 M&M, for this calculation that I'm doing, it's kind of a ballpark figure, of course, it's not exact, but let's just say the volume of 1 M&M is about a cubic centimeter. It's probably a little bit of a overestimate, but that's fine. All right, and then let's say what we do know from geography is that the area of the United States is about 3 million. I don't know if that's probably the contiguous United States, but again, we're not geographers here. So that's about 3 million square miles for the area of the United States. So what we're going to do is we're going to figure out, okay, we need to use a mole of M&Ms. 1 layer is this many square miles, and then use the volume and some geometry to figure out. So what we would find is that the height of the M&Ms, let's not talk about the number of layers, let's talk about the height of that first. Any guesses on this one? So if you said 20 layers, you're looking at maybe what? 10 inches or so at the most, or maybe 5 or 10 inches. Anybody have any other guesses besides a few inches?
20 feet.
20 feet. All right, we're getting a little bit closer, but it's actually going to be 50 miles. So it's huge, right? So the number mole is just gigantic. And that corresponds to 8 million layers. Now, hopefully this convinces you that there's not anywhere close to a mole of M&Ms in the whole world, but if there was, and you wanted to cover the whole United States with them, you'd have to go over the United States 8 million times before you finished one mole of M&Ms. So it's just absurd how big that number is. And the reason it's so big is because it's referring to things like atoms and molecules that are exceptionally tiny, so tiny at a scale that we can't even easily comprehend it on this, length scale that we're used to. All right, and then here's another one that's kind of cool. How many teaspoons of water are there in all of the world's oceans? So let's see how many that comes out to. So again, imagine you're going to empty out all the water in the world and just take it out 1 teaspoon at a time. How many teaspoons would you have to do? So again, I'll give you some of the inputs here, just if you wanted to try these calculations yourself, just factor, label, unit conversion stuff, but don't really worry about it too much. So there's 1.3 times 10 to the 9th cubic kilometers of water in all of the oceans, a huge number, of course. And what that corresponds to in teaspoons, so if you convert cubic kilometers into teaspoons, just a unit conversion, it's about 2.65 times 10 to the 23rd teaspoons. So there's basically 1 mole teaspoons of water in all of the world's oceans. So again, that tells you how big that number is. If you take out the water's ocean 1 teaspoon at a time, you have to do that a mole times to get all the water out. So it's a huge number. All right, so that was hopefully a little bit entertaining, but not going to be something that we're going to directly use in this course. But just gives you an idea that a mole Avogadros number in particular is just a huge number. But how do we actually use it, and why do we care about it in chemistry? Well, we care about it for a lot of reasons, but the first thing is we're going to see how it relates to the atomic mass, what we just defined and covered earlier today. And so an alternative interpretation of atomic mass, we gave it originally in AMUs, atomic mass units, basically saying that, okay, this is a mass unit that is on the scale of 1 proton or 1 neutron in the nucleus, and then each atom has a mass in AMU that corresponds roughly to its mass number. But the alternative interpretation of atomic mass is that it represents the mass in grams of 1 mole of that element. All right, so that's another way to think about the atomic mass. So we calculated the atomic mass of boron earlier as 10.81 AMU, but the other way to think about that is that there's 10.81 grams of boron in 1 mole of boron. So that atomic mass can also be thought of as the number of grams in 1 mole. And for our purposes, what we're going to be doing in the next 2 chapters especially, that's going to be the more useful way of thinking about atomic mass. And so what we're going to be doing a lot in this chapter, especially in chapter 6, but really through the next 4 chapters of this course, are a lot of conversions, a lot of converting amounts of substances into different units and things. And so right now, just with our definition of the mole and with the relationship to atomic mass, we now have already 2 conversion factors that involve the mole as one of the quantities. So from Avogadros number, we have 6.022 times 10 to the 23rd, and that's going to be usually atoms or molecules, or more generically things that make up 1 mole of that substance. All right, so I think that's something that's a little bit important to try to understand from the get-go. What exactly does this 6.022 times 10 to the 23rd refer to? Well, it refers to the fundamental building block that makes up that substance. So if we have carbon, which is an element, or any other element on the periodic table by itself, this would mean that 1 mole of that element has 6.02 times 10 to the 23rd atoms, because elements are made up of atoms. But if we had a mole of water, which is an H2O chemical formula, each molecule is H2O, there would be 6.02 times 10 to the 23rd molecules in 1 mole of water. So it's whatever the building block is for that substance, that's how many of those things are in 1 mole. So it's important to keep that straight when we're using these and doing conversions with them, as we'll start doing a little bit. And then the other unit conversion that we have that involves the moles is that if we have the atomic mass of an element, in grams, that's going to correspond to 1 mole of that. So that's, again, another ratio or conversion factor we can use involving moles. The mass in grams of an element for its atomic mass is equal to 1 mole. All right, so those are 2 conversion factors. So any questions on the background so far before we do a bunch of practice problems? All right, so what we're going to be then doing in Chapter 5 is sort of progressively more complex calculations involving moles. So we're going to just do a bunch of examples here of different ways we can set this up. Again, we don't have too many relationships yet, so there's not too many ways we can throw it at you. But let's do the first one. So here we have a helium cylinder becoming more and more precious as the years goes on. So I encourage you not to use it for balloons anymore. We need it for other more important purposes like MRIs. But anyway, helium cylinder contains 239 moles of helium. How many helium atoms are in there? So again, this is where when we do conversion factors, we think about the relationships we have involving moles. So we're going from moles to number of atoms, and so that is going to be a direct, simple one-step conversion. So when we set up problems like this, we've done some things with this sort of method, but we're going to be using it all the time in these next few chapters, this sort of factor label method. So what I like to do is write out what we're looking for first. So go usually to the last sentence of the question to figure out what it's asking you for. How many helium atoms are there? That's what we're looking for. And then we start the calculation with the quantity that we're given, which is 239 moles. And so then from there, we just need to figure out in one or more steps, how do we get from this quantity to that quantity? Well, we just define the mole as the number of atoms is 6.02 times 10 to the 23rd atoms in 1 mole, so we can use that number directly in one step. So we want moles to cancel out. Let me write it as moles of helium, just to be more specific. So we want moles of helium to cancel out, and then we want to find how many helium atoms are in there. So it's important and helpful to write out the units when you do these types of problems so that we know, do I multiply by Avogadros number? Do I divide by Avogadros number? If you're just writing out the numbers, which I know some of you do, I've seen it, it's going to sometimes hard to keep track of whether you should multiply or divide. But here, if we write it out this way, we know that we need moles to cancel out. So the definition of a mole is 6.02 times 10 to the 23rd things, in this case atoms, in 1 mole. So we're going to multiply by it in this case. And that just comes out to 1.44 times 10 to the 26th helium atoms. All right, and so the takeaway message from this problem is that when you're counting atoms or molecules, if we're asking how many atoms or how many molecules are there, you're always going to want to use Avogadros number as part of that, if we ask you for how many there are. And the other important thing is when you're using Avogadros number, it doesn't matter what substance it is. So this is helium, but if we had done the same calculation for any other element on the periodic table, carbon, nitrogen, oxygen, whatever, it would just be the same calculation. Avogadros number applies to all substances. It's not specific to any one element or compound. So the identity of the substance doesn't matter in this case. You have to know sort of what the fundamental particle is. Is it an atom or a molecule, to be able to sort of clearly define what you're talking about. But the numerical part of the calculation doesn't really depend on what substance it is. It's just Avogadros number, which you'll use for any substance. Okay? All right. Now, we'll have a lot of problems that involve this, in this part of the course, where we're asking you how many atoms or molecules are there and using Avogadros number to get to that. I mean, in reality, in chemistry, we don't usually need to talk about how many individual atoms or molecules there are. Like what is really the benefit of knowing that this entire cylinder has 1.44 times 10 to the 26 atoms? As we said, it's just a huge number, so we're not going to be able to really count that or measure that in any way directly anyway. But nonetheless, we want to use this definition and understand it. All right, so let's go on to another one. One of my favorite elements, which is gold, not only because it's valuable, but because it has a lot of cool chemistry too. But if we just have a gold coin, those have 31.1 grams of pure gold. How many moles of gold are in the coin? All right, so in this case, we want to find number of moles. So again, look at what it's asking for first. We're looking for the moles of gold, which has symbol AU. And then we write out what we're given, which is 31.1 grams. So whenever we're doing problems that involve conversions with moles, we have to always be aware of, okay, is there a single step conversion that gets me from, where I'm starting to where I'm going to, or do I need to do more than one step? Here again, we have a single step because we know that the relationship between grams and moles is the atomic mass of that element. All right, and so that's what we're going to use as the atomic mass. But again, to know whether we multiply or divide, it's helpful to write out the units that we're trying to convert into. So we're trying to find how many moles of gold there are. So we want that on the top, and we want grams to cancel. That's going to be at the bottom. And so the relationship grams per mole is the atomic mass. Now, we didn't give you the atomic mass here, but for any element, we can now look it up from the periodic table. So if we go back to the periodic table and find gold, which is still on the screen, luckily, but there it is, number 79, that number below 196.97 is the atomic mass. So we're going to start using those numbers now straight off the periodic table. So that's the atomic mass of gold, which is how many grams are in 1 mole. So this is how we're going to write out. We're going to put that number in the denominator, because the definition of atomic mass is 196.97 grams in 1 mole. And we want grams to cancel out, so that number has to go in the bottom. All right, so when we divide those two, we get 0.158 moles of gold. And so the key takeaway then from this type of problem, this is a very simple one, of course, but something that we want to always keep in mind when we're using atomic mass is that when we're converting mass to moles, you need to know the identity of the substance, and you need to use the correct atomic mass to do that. It's not any more independent of what substance you're talking about. So here it was important to know that it was gold so that we could use the correct atomic mass. If we didn't know what substance this was, there's no way we could do this calculation. All right, so that's just a couple of key differences between the two calculations that we've now done involving either Avogadros number or, in this case, atomic mass. All right, any questions on those ones? All right, so now we're going to do one that involves a couple of extra things. First is that we're going to have some unnecessary information given to you here, which we sometimes do, not because we want to trick you, but because we want you to start thinking like scientists and understanding which information is necessary. But also, this one's going to, as we'll see, is going to involve more than one step. So we have a nanoparticle that has a 1.3 nanometer diameter. So basically it's just a cluster of atoms. There's other things in there too, but it has this diameter. And it has, they did a really detailed structure of this, which is actually pretty rare for things on this dimension. But they found that there was 37 indium atoms in there. In is the atomic symbol for that. So we want to know what is the mass in one of these particles. So what we're doing here, there's a lot of information to sort through. First of all, I think what we should recognize is that this number here is just a total throwaway. We don't really care how big the particle is. We know how many atoms are in there, and we just need to convert that into mass. The size of the particle in terms of its dimensions is unimportant, so that we can ignore. But what we're again doing is we're going to start with what we're asking for, which is the mass of that element. And what we're starting with, which is how many atoms there are. So there's 37 atoms of indium. We want to know what the mass of those is in grams. Now we don't have a direct conversion factor from atoms into grams because we don't know the mass of one atom of indium. We just know the mass of 1 mole from the atomic mass. So this is going to be one that involves 2 conversions. So when you're doing problems involving moles, basically starting now up until the next few chapters of this course, the advice that I always give, which you're going to get tired of hearing though, is when in doubt, convert to moles first. So that's what we're going to do here. We don't have moles as either of our inputs or what we're looking for. So let's convert to moles first and see where that gets us. So what we're going to do is we're going to convert to moles. And so if we know how many atoms there are, that's going to be Avogadros number is the relationship there. So we want atoms to cancel out, and we're going to go into moles of that substance. And that's going to be Avogadros number. We know that there's 6.02 times 10 to the 23rd atoms in 1 mole. All right, so that gets us to atoms. And as I've always said, it's very helpful to write out the units when you're doing this because we don't want to stop here because this is still moles and we're looking for mass. We haven't gotten there yet. So this is when we're going to have to do a second step now. And the relationship between mass and moles is one that we've also covered today. So we want the moles to cancel out. So I do have to go to a second line. I can't always fit these in one line, unfortunately. So try to follow along and get used to that. So we want moles to cancel out. We want grams to be in the numerator. So that's going to be the atomic mass, grams over moles. So we have to find that in the periodic table for In, which is indium, pretty close to gold. Up here, a little bit higher though. And so the atomic mass of indium is 114.82, that number there. So we're going to use that number, and it's going to go in the top this time, so that we can convert into grams and have moles cancel out. All right, so that gets us to grams of indium, which is what we're looking for. I guess I wrote it as mass, but it's really the grams that we're looking for. So that's the unit. And so that comes out to 7.05 times 10 to the minus 21 grams. So it's an exceptionally tiny number because we're only talking about a very small collection of atoms. 37 is not a lot, and each atom has a very tiny mass. So that number might look a little bit jarring to you, but that would be the correct number for that small collection, 37 atoms that we have in this one particle. All right, so this was a problem where we had to do a two-step conversion. We only really have 2 steps at this point, so that's probably as high as we'll go for now, but there's going to be problems later on in this chapter and the following ones that require even more than 2 steps, so keeping track of the units and knowing the key relationships that involve moles is going to be really important for doing those. All right, any questions before I move on? Doing okay on time. All right, so let's move on then to another one that involves multiple steps. So here we have more gold, a gold bar this time. So I'm certainly not wealthy enough to own one of these, but I don't know if anybody else in the room is. But this is a lot of gold, so this would cost a lot of money. What is gold now? It's like at least 1,000 per gram. So this gold bar that's like 12,000 grams times 1,000. That's probably like, I don't know, at least hundreds of thousands of dollars worth of gold or something like that. It's a lot. I can't do the math in my head, but I don't have that much. But anyway, if we had, in the Fort Knox or wherever they store all the gold now, if you have a gold bar, it weighs 12.4 kilograms in a standard gold bar. So let's figure out how many gold atoms are present in this. And again, this is going to be a multi-step problem, but if we write out what we're looking for first, which is the number of gold atoms, now we write out our starting point, which is the mass, but this time in kilograms, we can go from there. All right, we have to again remember that we don't have a relationship that directly gets us from mass to number of atoms or vice versa. We have to go through the mole to get there. And so the first thing we're going to do is try to convert this quantity into moles, and that's going to itself be a 2-step because our mass relationship that involves moles is grams per moles, not kilograms per mole. So we have to convert to grams first. We don't use kilograms a lot in chemistry, but if we do, we have to get it to grams. So we want kilograms to cancel and grams to be what we end up with. So there's more than one way to write this, but the most straightforward way is there's 1,000 grams in 1 kilogram. So we won't use these prefixes a lot for the rest of the course, but make sure you still know the common ones like kilo. All right, so that gets us to grams, and then we can use that to get into moles now. And want grams to cancel out, so that's going to go on the bottom. So grams per mole is the atomic mass. We looked it up earlier. It's 196.97 grams of gold in 1 mole. All right, so that gets us into moles, but again, we have to make sure we don't stop these problems too early, and so we're not looking for the moles of gold, we're looking for how many gold atoms there are, individual atoms, so we have to do the one more step using Avogadros number. So we want moles to cancel out, and we want gold atoms on the top, and so that's going to be Avogadros number, how many atoms in 1 mole. So 6.02 times 10 to the 23rd is going to go in the top, and that's per 1 mole. So moles cancel out, and that gets us into the number of gold atoms that we have in this, and that's where we'll stop then. Okay, so that's going to be 3.79 times 10 to the 25th. So again, we're talking about the number of atoms in a sample. Usually that's going to be a really large number, especially for something like a big gold brick, and that's the number that we would get. All right, so any questions on that one? All right, so we've gone through pretty much every variation we can have at this point for converting between mass, moles, and number of atoms. So now we're going to take it one little step further. This is really not too much different, but we're going to define more generally what is called molar mass. So we've talked about atomic mass, which is the relationship for an individual element. But what if we have a compound that's made up of more than one element? So for that, we use what's called the molar mass, which, as the name implies, this definition is kind of stupid because it's exactly what the name of the term is, but it's the mass of 1 mole of a compound. So just like atomic mass, it's going to be in grams per mole. And we don't want this to be sort of confusing for anybody, but there are other ways of, naming this term. It's not always called molar mass. Molar mass is the most general and is pretty descriptive. It's this mass of 1 mole. But you might also see it given to you as, molecular weight. I mean, technically, molecular weight only works if it's a molecular compound, but you'll still see that a lot. Or sometimes it's called the formula mass or formula weight. And a common abbreviation, since molecular weight is so popular, would be sometimes MW. I don't think we do this anymore. The old textbook had this, but we've kind of filtered this out at this point. I can't even write it very well. They used to use this like big script M as the abbreviation. But the point is, if you see grams per mole, that's what we're talking about. Whatever the name that is given to it, it's going to be just the mass of 1 mole of that compound. All right, so how do we calculate it? Because, again, the periodic table directly gives us atomic mass, but there's not, substances on the periodic table. Well, it's pretty simple to do. We just have to add together the individual atomic masses from the chemical formula. So we know the chemical formula of the compound, all the elements that are in there. We know their individual atomic masses from the periodic table. We just have to add them up, accounting for how many of each of those elements is in the formula. So that's how we calculate molar mass for any substance. All right, so let's go through and just do an example of how to calculate molar mass. So you've probably heard of glycine if you've taken biology or biochemistry. It's an amino acid, so it's probably the simplest amino acid. And it has the chemical formula C2H5NO2. So what would be the molar mass of this substance? So when we look at a chemical formula, there's also 2 ways to interpret that. We've talked about in chapter 3 molecules. You have, that's usually in our case, a central atom, outer atoms, all that stuff. And we would say that 1 molecule of glycine has 2 carbon atoms, 5 hydrogen atoms, 1 nitrogen atom, and 2 oxygen atoms. That's what the chemical formula tells us. But the other way to interpret the chemical formula is that if you have 1 mole of this, C5H5NO2, that contains 2 moles of carbon, because there's a subscript of 2 by C, 5 moles of hydrogen, 1 mole of nitrogen, because there's no subscript by N, and then 2 moles of O. So we can interpret chemical, I wrote MOL for some of them, and moles for other. The abbreviation for moles is MOL, which is really dumb, because it's just like 1 letter difference, but anyway, those should all be MOL. Let's do that consistently. All right, so that's another way to interpret the chemical formula. And so then what that allows you to do is when you calculate the molar mass, you just have to add up the mass of 2 moles of carbon, 5 moles of hydrogen, 1 mole of nitrogen, and 2 moles of oxygen to get the mass of 1 mole of this compound. So it's, again, just adding up all the atomic masses. So the molar mass of this compound then is, we have 2 carbons in the formula, so we're going to multiply that atomic mass by 2, and we have to look up the atomic masses for C, H, N, and O on the periodic table. So those are all up here for the most part. So carbon is 12.011, nitrogen is 14.01. We only really need 2 decimal places, is perfectly fine. Oxygen is 16, and then we have hydrogen way up here, which is 1.01 or 1.008, however many decimal places you want to use for hydrogen. All right, so those are the 4 elements. So we have their atomic masses from the periodic table, which I'm not going to flip back and forth to a million times, but then we just multiply each of those atomic masses by the number of moles of that element that's in the formula. So there's 2 moles of carbon, so we're going to multiply its atomic mass by 2. So that's carbon. We have 5 moles of hydrogen, which has an atomic mass of 1.008 if you want to go that level of precision. That's hydrogen. we have 1 mole of nitrogen in the formula, and its atomic mass is 14.01. So that's nitrogen. And then there's 2 oxygens in the formula, and its atomic mass is 16. All right, so that's what we're going to multiply together and add up, and what we get is 75.07 grams per mole. So that means 1 mole of glycine would have a mass of 75.07 grams, and we got that just by adding up all 4 of the atomic masses, accounting for how many of each of those is in the formula. So it's pretty straightforward to do. All right, we can do, I suppose, one more example here. Determine the formula mass of lead-4 sulfate. All right, so we have lead-4 sulfate. So you have to get the formula for this first. So we can't forget everything we already learned, because sometimes we'll be describing substances in problems in this part of the course where we don't give you the formula of the compound. You have to come up with a formula. So if it's a simple ionic compound or an acid or a binary covalent compound, all the stuff we talked about in chapter 3, we can give you sometimes just the name of it, and you have to come up with the formula first before you can calculate its molar mass. So that's exactly what we're doing here. So lead-4 sulfate. So in this case, we have the number in parentheses tells us that the charge on the metal is +4. And then sulfate, we have to remember from our polyatomics, is SO4 2-. So to get the formula for this, we have a +4 charge on the metal and 2- on the sulfur. So if you want to do the no-brainer way of just crossing those, you would get initially lead-2 SO4 4, but that's not the smallest ratio. I always want the smallest ratio, so really the best way to write this is PbSO4 2. Okay, so that's the correct formula for that compound. Make sure we get that first. Again, you need 2 -2 anions to balance the charge from the +4 cation, however you choose to think about that. So now that we have the formula, we can go forward and get the molar mass, or what's called formula mass here. We use formula mass a lot for ionic compounds, but again, they're interchangeable for the most part, or really in reality they are interchangeable. So the formula mass, we account for how many are in the formula. So we have 1 lead in the formula. There's no subscript by lead, so there's just 1 of them. So for lead, there's 1, and we find this atomic mass. Pb is way over here somewhere in the P block. It's there, number 82. So 207.20 is the atomic mass of lead. So we're going to use that first. And then what we have to be a little bit careful with some ionic formulas that have polyatomics is to make sure we count the number of atoms correctly. So SO4 2 tells us that we have 2 total sulfate ions. So we have, each one has 1 sulfur and 4 oxygens, but in total we're going to have 2 sulfurs and 8 oxygens because it's SO4 taken twice. So to make sure we count those correctly when we're doing formulas like this, that's another reason to go through this one. So we have 2 sulfurs in the formula, so that's what we add up next. So this is lead, and then sulfur is 32.07, but if you don't believe me, let's go look it up. Yep, 32.07 for sulfur. So that's going to be that one. And then the last is oxygen, which, as we said, there's 8 of them because it's SO4 taken twice. So each one is 4, but there's 2 of them total, so we're going to have 8 oxygens. And as we just used earlier, that's 16 grams per mole for oxygen. So we add all those up together, and assuming I didn't mess up my math, you should get something like 399.34 grams per mole. All right, so getting molar masses, formula masses, it's relatively straightforward, but you have to get the formula correct in situations where we don't give you the formula like we did here. All right, I'm clear on that? All right, just a few more then. All right, so now we're going to do a slightly more complex example using the molar mass as part of that. So we've talked about gold, which is my second favorite element, and now we have iridium, which is my absolute favorite. You guys should all have your own favorite elements too if you don't already. So an iridium compound this was from a long time ago, this is kind of dated now, but this is what it looks like. It glows bright red, it's pretty cool to look at. But it has a molar mass of 774.94 grams per mole, so a pretty big molecule. how many molecules of this compound are in a 1 gram sample. So this is very similar to some of the problems we did earlier with elements. Now we're just doing it for a compound, where we're going to again use now the molar mass as the relationship between mass and moles for any compound. So what we're looking for is how many molecules there are. And what we're given, we're really given two things. We're given the atomic mass or the molar mass, and we're given the mass of the compound. So there's always sometimes a question like, what should my starting point be? Well, typically we're going to use molar masses and things like that as conversion factors. So you want to start with an actual quantity of the substance that you're given, which will be 1 gram in this case. So we have 1 gram of this compound. I'll just label it as iridium in brackets. We don't have the exact formula for this compound, but we don't need it for this problem. So we have 1 gram of the compound, and we're trying to find out how many molecules there are. But again, we don't have a direct relationship that goes from mass to number of molecules, so we're going to go through moles first. So we want grams to cancel out and convert into moles. As I said, when in doubt, convert into moles first. That's what we're going to do here. So we want the molar mass as grams per mole, so we're going to put that number in the denominator here, because that goes with grams. That's how many grams of the compound are in 1 mole. So grams cancels out, that gets us moles. But we're looking for how many molecules there are, not how many moles there are. So we have one more step, which is Avogadros number. So we want moles to cancel out. And we want to find how many molecules there are. And that's going to be Avogadros number of molecules in 1 mole. So that cancels out moles there and tells us how many molecules are in the sample. So it's really the same exact concept as we did before with some problems involving elements, but this time it's molar mass instead of atomic mass, but we interpret it the same way. It's the number of grams in 1 mole of that substance. So you get 7.77 times 10 to the 20th molecules. Again, whenever we ask you to calculate how many atoms or molecules there are, typically it's going to be a very big number because atoms and molecules are very small. All right, we're good on that? Any last questions? All right, the last thing we're going to review today, well, it's sort of a review and then sort of seeing how what we learned today relates to it, and then we'll take it forward next time in a slightly more complicated way, is the relationship between what we've learned today, mass, moles, atomic mass, molar mass, and mass percent. So we covered mass percent as one of the very first topics in this course, if you can remember back that far. It was just on the exam, so hopefully you haven't totally forgotten it. So mass percent was one of the key aspects of the mass laws that we covered. So it is especially relevant to the law of definite proportions, where we said that each chemical compound is defined by a specific mass percent of all the elements in that compound. So that was something that we had covered a long time ago. So as a review of that, remember that we defined mass percent is the mass of an element in a compound, which I'll just generically call element A, divided by the mass of the compound and then multiplied by 100 because it's a percentage. So the stuff we've done until now, we didn't know what a mole was. We didn't use moles, of course. And so everything involved, we had to actually give you these masses for you to be able to calculate this. We didn't do a lot of numerical problems involving mass percent, but there were some, and it always just involved, okay, here's the mass of the element, here's the mass of the compound, use those as a relationship, or calculate a mass percent, or do something with those. But what we have now, though, is the ability to use the molecular formula of any compound, the chemical formula in more general terms, to be able to calculate the mass percent of any element in that compound. So we don't need to be giving you masses directly, we just need to know the formula, and from there we can work our way towards the mass percentages. So the way that this works is, if we assume that we have 1 mole of compound, so you have to remember that mass percent is what's called an intrinsic quantity. It applies to however much of that substance we have. So if we have 1 molecule of that substance, or we have a whole mountain of that substance, is always going to have the same mass percent. It's an intrinsic quantity. It doesn't depend on the amount of substance we have. So we can assume any amount of substance that we want. So if we make the convenient assumption that we have 1 mole of a compound, we can then calculate the mass percent in a very simple way, which is by taking the mass of the element A in 1 mole of that compound divided by the molar mass of the compound, which is the mass of the whole compound in 1 mole. then multiply by 100. All right, because again, the denominator here, the molar mass of the compound, that's the mass of 1 mole of the compound. That's what it's defined as. And then the mass of the element in 1 mole, that's just sort of the piece of that element that goes into that calculation of molar mass. So whatever part of the molar mass came from that specific element is the mass of the element that's in 1 mole. And then the dividing of the two multiplied by 100 gives us a percent. So this is best understood with an example, which we'll close with today. This is the back. So I guess we're gonna get out a little bit early today. Hope you guys don't mind. So that's going to get us back to glycine again, which we calculated earlier, the molar mass of this compound. Now we're going to calculate the mass percent of carbon. We could do it for any of these elements. It has carbon, hydrogen, nitrogen, oxygen. We could calculate the mass percent of all 4 of those if we wanted to. It's a little bit tedious, so I'm not going to do all of that. But if you did calculate the mass percentages of all of those, it would add up to 100 if you did it correctly. But let's just do it for carbon here. So again, the way that we do these types of problems for mass percent is we're going to assume that we have 1 mole of the compound, which has this chemical formula. And as we calculated earlier, we're going to use, if you were starting this problem from scratch, you would need to calculate the molar mass like we did before. We already did that one a few slides ago, so I'm not going to do it again. But the mass of 1 mole of this compound is 75.07 grams. Again, we got that number by just adding up all the atomic masses. We did that a few slides ago if you want to look back at it. So that's the mass of 1 mole of the compound. If we want to find the mass percent of carbon, we need to figure out how much carbon is in 1 mole of this compound. And the key there is to look at the chemical formula and show that, okay, that 2 tells us that 1 mole of this compound has 2 moles of carbon. So to get the mass of carbon, we have to calculate the mass of 2 moles of carbon first. So the mass of carbon in this sample, 1 mole sample, we have 2 moles of carbon in the formula, because the subscript 2 tells us there's 2 moles of carbon per mole of compound. And we want to convert moles into mass, we just use the atomic mass like we learned earlier today. So we have to find the atomic mass of carbon. We did that earlier, but let's look it up again. Just get used to finding those. So again, carbon is 12.01 grams per mole. So 1 mole of carbon is 12.01 grams. And so for 2 moles, we just have to multiply that. 12.01 grams of carbon in 1 mole. Moles cancel out, and that gives us grams. So 1 mole of this compound has 2 moles of carbon, and the mass of 2 moles of carbon is 24.02 grams. All right, so now we have the mass of the element in 1 mole. We have the mass of the compound in 1 mole, which is this molar mass, and so we can just calculate the mass percent using the definition of it. Mass percent of carbon is 24.02 grams of carbon divided by the mass of the compound, which is 75.07 grams, multiplied by 100. So grams cancel out. They both need to be in the same unit, of course. And that gives out to 32.00%. So that means by mass, 32% of this compound is carbon. All right? And you can do it for any other element. For hydrogen, there'd be 5 moles. For nitrogen, there'd be 1 mole. Oxygen, 2 moles. Find out the mass of each of those, divide by the molar mass of the compound, and you get the mass percent. All right, so we finished a little bit early today. We'll pick up next time with more things involving moles and getting into stoichiometry as well.